Let's talk about radioactive half-lives. And so half-lives are normally given the symbol T with a little subscript 1/2. We might pronounce it T 1/2. And it is the time for half of the radioactive atoms to decay. So it's time for 1/2, so that's 50% if you like, or 0.5 of the radioactive atoms to decay. So they don't disappear, but instead they form that decay product. So in the case of iodine 131, which we looked at in the last lecture, if we started with, say, 1 gram of it is a beta decayer, and it has a half-life of actually 8 days. And so every 8 days, essentially, you only get half as many atoms as before. So after 8 days, you've got iodine 131, but you only have half a gram of it. Now, where did it go, right? You've got half a gram of the other substance, right, which I think we said was xenon 131. And again, if you wait another half day, so a lot of people think, well, 2 halves make a whole, but actually the half-life, interestingly enough, operates on half of what you get after the last half-life. So if you've got half a gram, then after another 8 days, you actually have half of a half. So half of a half is a quarter of a gram. And again, if you wait another 8 days, right, then you're going to have 1/2 of that. So that is 1/8 of a gram, or 0.125. And so it never actually goes away. So for a lot of processes, a lot of, say, labs, what they do is they say after 8 half-lives, essentially you've got half of a 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 half, which is basically, it's almost all decayed away. And I believe, I'm not a lawyer, please do not take this as legal advice, but I believe after 8 half-lives, legally you can throw out radioactive material, assuming the daughter products aren't radioactive as well. So if you ever have iodine treatment for a thyroid gland problem, after about 8 half-lives, after about 64 days or 2 months, when you go through the airport, you won't set off the radiation detectors because essentially it's decayed away to such a minuscule amount at that point. And again, if we go ahead and we draw a little graph, I'm going to draw a little graph down here of the percent versus time, and we know that at the start, right, we have 100% of whatever we have. Well, after 1 half-life, that is down to 50%. Okay, after 2 half-lives, whatever the material is, it's down to 25%. After 3 half-lives, right, it is down to 1/2 of that, 12.5%. After 4 half-lives or 5 half-lives, it looks something like so. And actually, if you like math, which I actually kind of like math, this is what we call an exponential decay. And so it never really quite reaches 0, but it decays off so quickly that after 7 or 8 of these half-lives, you're essentially almost at 0%. So it never really truly goes away, but it gets awfully darn close, I would say. One of the neat things about these atoms is that they all have their own unique half-life. So, for instance, carbon-14 has a half-life of almost 6,000 years, so 5,730 years. It is a beta decayer. That's kind of only of interest, really, I guess, if you're into that kind of thing. But we use it to date organic materials because you're constantly breathing in carbon dioxide, or if you're a plant and you're using it for food, and if you're not a plant, you're probably eating plants. And so there's a constant percentage of carbon-14 atoms in your body. And of course, the thing about dying is you don't tend to eat anymore, so they decay away. And every time you, well, I guess not every time you die, but when you die, every 5,700 years after you die, half those carbon-14 atoms decay away. After another 5,730 years, then another half has gone away. And so if you measure the percent of carbon-14 in a formally living thing, you can date it at least within about 8 half-lives or so about 40,000 years or so, fairly decently. I think we already said iodine 131 has a half-life of 8 days, so it is pretty darn fast. Something like uranium 235, though, has a half-life, I'm going to ditto that out, of about 700 million years. So you can date rocks or very, very old material here using this enormous half-life. So it never really quite goes away, but essentially after every 700 million years, half of it is gone. So how old's the Earth right now? 4 billion years, 5 billion years. So quite a lot of it's gone away, but we still have uranium-235. Otherwise, we wouldn't have nuclear reactors. And I would say at this point here, we're actually done with the course. So congratulations, we have made it through everything. I hope you enjoyed the nuclear lectures. I always kind of like them, actually. I think they kind of review some of those concepts from earlier on, and I think that really helps to kind of reinforce the material, especially the final exam, which is comprehensive, will ask back some of those old questions. So now you are prepared, and well done, you survived. Congratulations.